Hello everyone. We want to continue on the topic of capillary pressure, and we have talked about the capillary pressure and what is the equation for it. So we define the capillary pressure as the pressure that is required to push the non-fading phase into the capillary tube and displace the wetting phase with the non-wetting phase. So it's calculated based on the difference between the pressure of the non-wetting phase minus the pressure of wetting phase inside the capillary. I should mention that these two pressures are at the boundary of these at the phase boundary. So the non-wetting phase is inside the air, for example, in this case, and the wetting phase is water, and it's in the water phase. So this point is the pressure of the wetting phase, this point is the pressure of the non-wetting phase. Anyway, so the capillary pressure is calculated as 2 sigma. Sigma is the interfacial tension between the wetting phase and non-wetting phase. Cosine theta is the contact angle of these two fluids on the surface, and RC is the radius of the capillary tube. Now we want to derive an equation for this system. This system is a water oil system. So you can see there is a bucket. There is a capillary tube inside this bucket. There is oil here, and this is water. And what we want to do is to calculate the capillary pressure of this single capillary submerged in the oil and water. All right, so let's look at what we have here. So a couple of equations we can find by looking at this graph. The first one is that the pressure of this is the oil water system, of course, right? So the pressure at here, which is PO2, right? And the pressure here, which is PW2, these two pressures are equal to each other. So the pressure at this point and the pressure at this point are equal. The reason is that they are the same fluid, and these 2 points are in the same fluid. So I should mention this is exactly in water. So just at the boundary of these two phases. Okay, so yeah, so we have this PW2, right? So PW2 is equal to PO2. The reason that these two pressures are equal because these two pressures are exactly at the boundary of the oil and water phase. Which means that and there is no capillary here, so PO2 is equal to PW2. This is not a capillary, this is much larger than a capillary, right? So the pressure at this point at the oil phase is equal to the pressure at this point at the water phase, right? Okay, so PO2 is equal to PW2. Now we can write an equation for PW2, which is equal to PW1 plus rho WHG. So if you look at the PW2, right, which is here, and if you write the equation for this, you can use the PW1, right, which is the pressure at this point, exactly here, right? So whatever pressure is here plus the hydraulic pressure addition from this height of liquid, so that would be PW1, whatever pressure is being applied at this point, plus rho GHW, right? So this is basically HW, right? All right, so that's one equation. Another equation we can write is PO2 is equal to PO1 plus rho oil HG, right? So PO2 again is the pressure at the oil phase plus whatever height. So the pressure at this point and the pressure at this point are equal, right? So this is in oil phase, this is in oil phase. So, and they are hydraulically connected at the same height. So this pressure is equal to PO1. So you can say that PO2 is equal to PO1 plus the hydraulic pressure of this height of oil, right? Which is this equation. All right, and sorry, this height of the oil, right? Because PO1 represents this much of oil plus whatever atmospheric pressure is, and you have to add this pressure to this height, which is again exactly HW. So we have these two equations, right? And since we know that PO2 is equal to PW2, we can basically put these equations equal to each other. So we say PW1 plus rho W HWG is equal to PO1 plus rho oil HG, and we can say that PO1 minus PW1 is equal to rho W minus rho oil multiplied by HG, and this is the definition of capillary pressure, because in this case you can see still that the water is the bedding phase. So oil is the non-bedding phase. This is pressure of the non-bedding phase minus the pressure of the bedding phase. Therefore, you can say that this is capillary pressure equal to the density difference of oil and water multiplied by the height of the water inside the capillary multiplied by gravitational acceleration. This is another important equation. So if you have two phase and you have submerged the capillary tube inside, and you have two phases, which is very close to what we have in porous media, this is how you calculate the capillary pressure. All right, so just to wrap up, the first equation was PW2 is equal to PO2. The reason was that there is no capillary pressure here, and we are measuring the PO2 and PW2. They are exactly at the same depths. So if I just magnify that part, PO2 is here, PW2 is here. Okay, so they are basically at the same point but in different phases. So since there is no capillary pressure here, the radius is really high. It's like a bucket of water. So there is no capillary pressure at this point. So PW2 is equal to PO2. Another equation was PW2 is equal to PW1 plus rho GH. So we calculated this PW2 equal to PW1 plus whatever pressure is being applied to this point, which is PW1, right? We have to add this hydraulic height. And finally, we had PO2, which was the pressure here, that is equal to PO1, which is equal to this point, and this pressure is equal to this pressure. PO2 is equal to PO1, whatever pressure is being applied here, plus the hydraulic pressure of oil in this, which is rho GH, rho oil GH, right? So these two are equal to each other, we mentioned. And this is the third equation. So from equation 1, we can see these two are equal. So these two equations, we put them equal to each other. And by some simplification, we can find the capillary pressure for this case. So we continue on this topic in the next video.